thanks for all being here. My name is Renske, I'm from the University of Zurich, and today I will tell you a little bit about the evolution of functional traits, the colonization of new biomes, and how these may affect diversification rates in Rhamnaceae. And in this study we try to disentangle the direct and the indirect triggers of radiations or diversification rate shifts. And we hypothesized that the interaction between extrinsic opportunities and the evolution of intrinsic traits triggers diversification rate shifts. So for example, the colonization of a new biome could be such an extrinsic opportunity. And together with the evolution of certain typical traits or adaptations, this may lead to a rate increase as detected on a phylogeny. So this idea is not entirely new. It follows the ideas of George Simpson, who already said that radiation follows the occupation of an adaptive zone, which is made possible by, first of all, physical access or dispersal colonization of this zone, evolutionary change, later called key innovations, and ecological fortune. So the zone must be empty, such as the sky was for birds when they evolved the ability to fly, or competition poor. So all of these factors probably have an effect on radiations, but can we disentangle which of these are direct and which are indirect triggers of the radiation? So we can think of a couple of different scenarios. For example, a lineage can colonize early in its history a new biome, but only later it evolves these typical traits, and the moment it evolves these adaptations, the radiation starts. Alternatively, it can evolve these traits early in the history, but only when it colonizes a new biome and has this ecological opportunity, it starts the radiation. These two can also interact and happen at more or less the same time. We call this a compound trigger of a radiation. And then there's a couple of alternative scenarios where these traits and a new biome could affect diversification rates, but they're not directly linked to the rate shift, or they evolve afterwards. So we test these different scenarios in the Rhamnaceae, in the order Rosales, which have a worldwide distribution as indicated in red here. They have about 1,000 species, and possible radiations could be in Mediterranean-type ecosystems where they are very dominant. So we recognize 5 of the regions in the Mediterranean basin, in South and Southwestern Australia, in the Cape Floristic region, in Chile, and in California. So throughout the presentation, when I talk about Mediterranean shrublands, I sometimes call them MTE. So to disentangle these direct and indirect triggers of radiations, we ask 3 questions. First of all, can we detect any diversification rate shifts in the family? Second, which extrinsic opportunities and intrinsic traits are associated with increased rates of diversification, so could be possible triggers of the rate shifts? And what is the temporal sequence of events? So when did extrinsic opportunities arise, when did they evolve to intrinsic traits, and when did the rate shifts occur? So the possible extrinsic triggers we look at are mainly in the form of vegetation type. So we distinguish open and closed vegetation. And within open vegetation we recognize Mediterranean shrublands, such as Fidica, which occurs in the Cape Floristic region. Desert biomes or savanna, such as Sisyphus. And in closed vegetation we recognize rainforests, such as Adolphia, which occurs in the tropical rainforest in Australia. For the intrinsic traits, we mainly look at vegetative traits, so different leaf traits, such as low SLA, where SLA stands for specific leaf area, and it's the ratio between the area of the leaf and its weight. And you often see when leaves are sclerophilous or hardy that they have a low SLA. And this trait is also correlated to a range of other traits in the leaf economic spectrum. We look at leaf size, the presence of revolute leaf margins, which means that the margins are curled under the leaf. Tooth or entire leaves, deciduous or evergreen leaves, the presence of spines, and different types of growth form. So to this end, we built a phylogenetic tree for Rhamnaceae for 280 species, based on 6 chloroplast markers and ITS, and we estimated divergence times using BEAST and 8 fossil calibrations. And we can see that the Rhamnaceae are about 90 million years old. The main tribes in the family are monophyletic, and the main diversity arose during the Cenozoic in the last 65 million years. So we use this tree to see if there are any diversification rate shifts in the family. And we use BEM for this, which detects shifts in diversification rate regimes on the phylogeny. using a Bayesian method and comparing different models where the shift may have occurred with base factors. And we find 4 most probable shifts indicated here. And if we plot the diversification rate on the y-axis and we compare it to the background rate, so over here, which is all the black lineages, we find 2 increases in rate in the Phylica, so in the Cape Floristic region, and in the Pomaderia, which is an entirely Australian clade. And we find 2 slowdowns in the net diversification rate, but these actually have high speciation and high extinction rates, so it's a clade with high turnover. In Cyanothus, which occurs in California, North America, Mexico, and in the Rhamnaceae and Frangula, which occur throughout the Northern Hemisphere. So which extrinsic opportunities and intrinsic traits are associated with increased rates of diversification? We use the BC algorithm in the diversity tree package in R, which estimates speciation, extinction, and transition rate for a trait with binary states. For example, presence or absence in Mediterranean shrublands. And we compare different models to see which parameters should be included. And then we had sampling proportions for species not sampled in the tree and their state for the traits. So if we look at the net diversification rate and we get probability densities for in blue presence of the trait, so presence in MTEs, and in yellow absence in MTEs. And we say that if these intervals do not overlap, they are significantly different. So we find higher diversification rates for lineages occurring in Mediterranean shrublands compared to lineages absent. And we find the same, for example, for lineages with low SLA leaves, which have higher diversification rates, and lineages with high SLA leaves. So these are 2 examples, and we can fill in a table for all our extrinsic and intrinsic traits and whether they have a positive or a negative effect on the diversification rate, and whether this is significant. So then we look at the temporal sequence of events. So for this, we look at each rate shift separately. So as you remember, BAM detected a rate shift in Phylica, which occurred at this node. So for all those traits that were significant in BC, we performed ancestral state reconstructions. And here, for example, for presence or absence in MTEs. And then we look at those nodes, only those nodes leading up to the rate shift. And we plot the probability of presence in MTEs on the y-axis. The x-axis here is time, so the same timeline as used in the tree. And these arrow bars indicate 95% HPDs of the estimated node ages. So then we look how the probability of this trait changes through time towards the node where the rate shift occurred. And we say that if the probability reaches an arbitrary threshold of 0.75, if this happens within the 95% HPD of the node where the rate shift occurred, it could be a direct trigger. So in this case, we conclude that because the colonization of MTE happens at more or less the same time as the rate shift occurs, it's a direct trigger. However, there are different scenarios. For example, open vegetation is ancestral in Rhamnaceae, so it happened prior to the rate shift. As said, Mediterranean shrubland could be a direct trigger, and the shift to desert only happens after the rate shift happened. And we find for different intrinsic traits that they all co-occur with the rate shift, so could be direct triggers, such as low SLA, small leaves, and revolute margins. So we look at each rate shift separately, Phylica, Cyanothus, the Pomaderia, and Rhamnaceae frangula. We look which traits co-occur with the rate shift, so could be potential triggers in red. We see which traits precede the rate shift and which traits follow the rate shift. And in X it means that this trait doesn't change from the ancestors to the rate shift or afterwards, so it doesn't have any effect on this rate shift. So then we can build a scenario for Rhamnaceae where we have our 2 rate increases in Phylica and the Pomaderia, and 2 rate slowdowns in Cyanothus and Rhamnaceae frangula. And we see that the ancestor of the Rhamnaceae occurred in a mix of open and closed vegetation, in rainforest, had spines and deciduous large toothed leaves. And then as a direct trigger of the Phylica shift, we see the colonization of Mediterranean regions and the evolution of a whole range of intrinsic traits and the loss of spines. And only afterwards they colonize the desert. And we can do this for each rate shift. So preceding the Cyanothus shift, there's the loss of spines. At the shift, they move to open and leaves become smaller. And afterwards they colonize the Mediterranean and evolve some intrinsic traits. Preceding Pomaderia is the innovation of some intrinsic traits. At the shift they colonize Mediterranean, they lose spines and leaves become evergreen. And after the shift they evolve low SLA leaves and revolute margins. Also preceding Rhamnaceae, there's the loss of spines. Nothing happens at the rate shift. And afterwards they colonize some new biomes and re-evolve spines. So, if we look at our two rate increases in Phylica and Pomaderia and two rate slowdowns, Cyanotus and Rhamnaceae frangula, and on the y-axis we have the number of possible triggers and how they change towards the rate shift. So here's the rate shift, and this is the timeline, and these are the nodes leading to the node where the rate shift is. We see that not much is happening in Phylica prior to the rate shift. And then at the rate shift, they colonize new biomes. They have a whole bunch of extrinsic opportunities and intrinsic traits all arising at the same time. Whereas in Pomaderia, we see a gradual accumulation of intrinsic traits, almost like they evolve some kind of trait syndrome, and when all traits are present, the rate shifts occur. And this gradual accumulation of traits is absent in Phylica, probably because there's a long stem lineage preceding the Phylica shift. If we look at our slowdowns or our high our turnover clades, we see that not much is happening prior to the shift. But after the shift, they suddenly evolve some intrinsic traits and colonize new biomes, almost like to compensate for the initiated slowdown. Of course, in this study, it's very important to score as many intrinsic traits and ecological opportunities as may have influenced the diversification of the clade. However, we can conclude that disentangling triggers for diversification rate shifts is complex, and already in one clade there is support for intrinsic, extrinsic, and compound triggers. And both environments and traits can provide the setting or background for these rate shifts, as well as being the direct triggers. And this probably means that each radiation is unique and has its own combination of intrinsic, extrinsic, direct, and indirect triggers. And that probably means that it will be very complicated to predict radiations. So with this, I would like to thank my funding and the help and input of several people. Thank you.